Hi guys, today we are going to learn about cyclic groups. Here are the contents we will see. First we will define cyclic subgroup, and then we will see cyclic groups, their examples and some interesting properties. Because we already know that if we take all the integer powers of an element of a group, it becomes a subgroup. So actually it's a very special subgroup that actually gives an idea to define a cyclic group. So what's that? We take an element from a group J, and then we take all the powers of that element. Then because it's a subgroup, and because here all the elements here are the powers of a single element A, so in that sense we call it a cyclic subgroup of that group J, and generated by, of course, A. So we use this notation, that is angle bracket inside A, so we call it a cyclic subgroup. And by AN it means that we have to apply the operation of group n times. In case the operation is addition, then we write this notation, that is NA, that is n times this A. Okay, here we have some examples. We consider 2 from the group of addition modulo 6, and we start computing the powers of 2. Here powers mean we have to start adding this 2 one time, 2 times, 3 times, and so on. So we see we will get 0 to 4, so we say it's a cyclic subgroup generated by 2. Similarly, in case of U10, if we take element 3, because it's a group under multiplication, so we have to compute the powers of 3 and with respect to multiplication, so we see we get nothing but 1379, so it becomes a subgroup generated by 3. Similarly, in example 3, and in example 4, it's very interesting example, because here we have a group S3 cross Z3. So if we take an element first, this x2, so it's actually an ordered pair where x comes from S3 and this 2 comes from Z3. So we see if we keep applying the operation of this S3 cross Z3, we get these elements. So we say it's a cyclic subgroup generated by this single element of the form of ordered pair x2. If we consider Z11 and take element 1, we see we get the entire Z11, so that's really interesting. So we see here in all the above examples we considered elements and they generated just a subgroup, but here we see we take an element and actually it generates the entire group. This actually leads to define the cyclic subgroup, that is a situation where a single element exhausts, generates the entire group. Okay, what's a cyclic group? As we just discussed, we have a group and then we say it's said to be a cyclic if it is generated by a single element. That is, if there is an element, we take the powers of that element, and if we get this equal to G, then we say it's a cyclic group, and this A is said to be then the generator of A. Okay, here are some examples. For example, if we consider set of integers, this under addition, then it's a cyclic group generated by this one. Interestingly, we note that -1 is also actual generator of this group. If we consider Zn, that is group under addition modulo n, then it is generated by 1. It is also generated by actually n-1 as well. So later we will generally see that if A is a generator, then inverse of A is also a generator. We will see later at the end. For example, if we take Z8, then 1 3 7 5, these are the generators of 8. So we also note that the generator is not actually unique, may not be unique, may or may not be. In these example we see the generator, there are more than 2 generators. Here is a non-example, that is U8. For example, if we take any element from U8, then actually it cannot generate this U8, so that's why it cannot be a cyclic group. Okay, here are some properties of cyclic groups. For example, the first one says every cyclic group is abelian. Okay, we consider a group which is cyclic generated by A, so this A is the generator of the, and we need to prove that it is actually an abelian. Okay, so we take 2 elements from the group and we need to prove that these 2 elements actually commute, that is xy is nothing but yx. Okay, when we take 2 elements, then by definition these 2 can be written as the powers of A, because A is the generator. It means x is nothing but A raised to L, and similarly y. If we start from here, xy, so we replace this xy by these representatives al and am. Now using the addition of integers, we can write in this way, and because the addition is commutative, so we can write this l plus m equal to m plus l. So we started from xy. After these steps we see we get actually yx, so these x and y, these were 2 arbitrary elements from G. So in that sense we can say this G is an abelian group. So the conclusion is, if we take any cyclic group, then it becomes an abelian. So here is about subgroup of a cyclic group, that is we have a cyclic group. So we want to know that what about its subgroup. This theorem says that if we have a subgroup of a cyclic group, then it is also cyclic. Okay, so we assume that we have a group G that is cyclic and is generated by some element, say A, and we consider H to be a subgroup of J. There are 2 cases. One is if this H is this trivial subgroup, that is consisting of only the neutral element, then it's quite simple because it's a neutral element. In case if H is different from this trivial subgroup, then because H is a subgroup, so all powers of A definitely will go to H, because it's a set of integers, positive integers for example. Because there is an order in the set of positive integers, we can choose the smallest possible integer. So we assume that this m, that's an assumption, this m be the smallest positive integer in this, because I repeat, because it's a set of positive integers, so there is an order. So there is an order. Please recall from the number theory course what is an order. So we are able to choose the smallest possible integer here. So we assume that this m is the smallest integer such that a raised to m goes to h. Now we claim that this element is actually the generator of h, that is h is generated by this element. So generated by this element means that all the elements in H, they are actually the powers of am. So just for simplification we assume that this am say is C. So we must show that every element in H is a power of C. Okay, because this B is coming from H and H is a subgroup of J, definitely B is some power of A because the underlying group is J, the generator was A, so every element sitting in G can be written as a power of A for some n, of course. So again, recall from the number theory course, there is a Devian algorithm. So we have integers m, q, r such that this m is equal to mq plus r. So it's exactly the by the definition of Devian algorithm. Of course, r is the remainder and it cannot exceed this m by definition. So if we replace this n by mq plus r, so you see finally we are able to write this ar is equal to this. So we see that an comes from H, am also comes from H, and it was a subgroup, so that's why by subgroup test these two elements they are in H, and consequently this ar belongs to H. Okay, but we assumed that m was the smallest positive integer for which am goes to H, because here by Devian algorithm this r was less than m, so the only possibility left is that this r must be 0. In that case this n would be qm, and we can write this b as am with raised to q, so it means this b is actually written as the power of am, and then we are done. Here is another interesting result. So in this theorem there are two things. So it's about order of A. So there are two parts. If the order is finite here, and if the order is infinite. So we have a group G, we take an element from J. If A has infinite order, then the powers, these two powers of A, they are actually same if and only if I coincides J. And the second part says if A has finite order, say we can assume of course n, then the group generated by this A is actually nothing, but it contains the powers of A, and the two powers they coincides if and only if this n divides the difference of I and j. So feel the difference here. So these two powers were same if and only if I equals j. So that was the infinite case, and in case of finite, the order is finite, then this happens if and only if n divides I minus j. Okay, there are two main parts. First we assume that suppose the order of A is say infinite, then by definition it means there does not exist any positive integer such that A raised to m is E. Okay, so when these two are equal, so the only possibility is that this I minus j is nothing but 0. In that case I becomes j. Okay, so look here, because the order of A is n, so by definition all these powers starting from 0, 1, 2 up to n minus 1, these are distinct, they cannot be same. None of these cannot coincide with any other. Okay, let's assume that suppose for some ai the power, for some aij, so ai is equal to aj with the assumption that I and j n minus is less than, of course, n minus 1. That is, we want to say that we assume, say some powers here, suppose they are same, then what happens? Then it would mean that a raised to I minus j is a. Definitely it contradicts, because n was order. N by definition is the least positive integer that produces a. Okay, now suppose a raised to k coming from this set generated by a, then according to Devian algorithm we can write this k as qn plus r, and of course this remainder cannot exceed this strictly, of course, strictly less than this n. If we replace this k by qn plus r, then we are able to write this as ar. So it means now ak is written as power of ar. Consequently, this a raised to k goes to the set of all powers of a. Okay, if we assume that now these, so we are in the second part where the order was finite. If we assume that ai is equal to aj, and of course we have to show that n divides the difference, then we can write ai minus j is a. Again, by Devian algorithm we are able to write in this form, and if we replace this I minus j by qn plus r, we see we can write all this equal to ar, because n is the least positive integer. Then it means, because n was the order, then it means if ar is also producing this a, then it simply means that r is nothing but 0. Okay, so if we replace here 0, then it means I minus j is qn. So according to division of integers, we can say this n divides I minus j. On the other hand, if we assume that, say, n divides I minus j, the difference of these two, then of course by definition of division there would be some integer q such that I minus j is nothing but nq. Okay, so replace this I minus j by nq, and we see we can write a and q, and finally it's e. And we see, starting from here, if we compare this first step with this one, so we see actually I minus j, because here e, because it's an e, so we can say that ei is nothing but aj, and we are done. Here we see some immediate consequences of this theorem. The first one says, if we take any element from the group, then the order of element and the order of the cyclic group generated by that element A, they are the same. So it directly follows from the above theorem. We can easily write just a one-liner proof here. In the second, we have a group, and we assume that A be an element of order n in G. Then what happens? Interestingly, if A raised to k is E, then n actually divides k. We will see some outlines of this proof of this theorem as well. So we have a group, and we assume that order is n, k is a natural number. Then the cyclic group generated by ak is actually the same as the cyclic group generated by the greatest common divisor of n and k. And the second part says the order of this ak is actually this fraction, n divided by the greatest common divisor of n and k. So there are two parts. For the simplification, we assume that d is nothing but this greatest the greatest common divisor of n and k. Okay, because a raised to k is actually a can be written as a d raised to r, so it means all the powers, all the elements here in the cyclic group generated by AK, they are actually contained into the cyclic group generated by A raised to D. Okay, recall the definition of greatest common divisor, because D is the greatest common divisor of NK. So recall from number theory that this D can be written as a linear combination of this n and k, that is, there would be some integer s and t such that D is the linear combination ns plus kt. So we replace this D by its linear combination. So these are just simple steps, and consequently we see we are able to write this ak as a power of k. So it means because it's the power of ak, so it means it would go to the set of all powers of ak, and consequently this the cyclic group generated by AD is actually contained into the cyclic group generated by AK, and by mutual inclusions we conclude that these two are same. In the second part, because D was the greatest common divisor, so D divides n, and consequently we are able to write this an is a. Okay, so look here, because this n was the order, so that's why it's a. So we see here the order of AD, the order of this AD cannot exceed this n by D. On the other hand, if we consider any natural number less than, then of course it cannot produce this A by definition of the order of A. So in that sense we can say this was the smallest, so that becomes the order of this AD. Okay, so order of AK is actually by above result, so order of AK is nothing but the order of the cyclic group generated by AK, and we just proved that these two are same, AK and D, and for the same reason. And now we see it's nothing but n by D, and D was the greatest common divisor, so we replace this by GCD of NK, and we are done. So here we have another interesting corollary, that if we have a finite cyclic group, then order of an element divides the order of group. Very simple, immediate, we can prove. And similarly the next corollary, so here we assume that the order is n, and the cyclic group generated by AI equals the cyclic group generated by AJ if and only if the greatest common divisor of Ni and Nj, they are same. And in the second part it's about order of AI and order of AJ. It's the same again for the same reason. Okay, here is another interesting property which is actually the corollary of the above theorem. So we assume that order is finite, then a cyclic group generated by A and a cyclic group generated by the power of A, these two are same if and only if the greatest common divisor of n and j is 1. In other words, if n and j, they are relatively prime. So we will use this corollary in the next example. This actually helps to compute the generators of the cyclic group. If we know, for example, one generator, then by using this corollary we are able to compute all other generators of that cyclic group. Okay, once one generator of a cyclic group is found, then all generators can then be easily determined as the following example shows. We consider U25. There are 20 elements. It's a group under multiplication. So we know 2 is the generator of this U25. Then we need to find actually the remaining generators of this U25. So we need to compute the powers of 2, but with those power which are actually relatively prime with 20. 20 is the order. So we see we will get, because it's a group multiplication modulo 25, so you see we will get 2, 8, 3 and so on. So we see there are actually repetitions. The distinct powers we get actually are 3, 8, 12, 13, 17, 22 and then 23. So these are the all generators of U25. Here we have some exercises. Interesting one. In the first case you need to find the generators of Z6, Z8 and Z20. In the second exercise you actually need to find a non-cyclic group, a group which is not cyclic, but the subgroups they are cyclic. Very interesting. So in the third part you have to actually prove that if A is a generator of a cyclic group J, then the inverse of that generator is also a generator of that group. So all the above learning material was borrowed from these two books, John B. Foley and Joseph A. Gallion. So we used actually these two books, and these two books are also recommended books for this course. So thank you very much.